Now that we've seen a basic encoding, let's turn our attention to encoding integers. And we're going to talk about both unsigned integers, positive numbers, as well as signed integers, integers that can represent both positive and negative values. Let's start with a basic example of binary number representation. Here we see an 8-bit value represented by 8 binary bits labeled B7 through B0, the most significant bit to the least significant bit. The reason we call them most significant and least significant is you'll notice that B0 is a coefficient on 2 to the 0 or 1. This represents the ones column of the number. And B1 is the twos column of the number. B5 is the 32s column. And B6 is the 64s column, and so on. A useful formula to remember is that if we have an n-bit quantity, then the largest number we can represent is 2 to the n minus 1. In the case of 8 bits, with n equal to 8, that would be the number 255, namely 128 plus 64 plus 32 all the way down to plus 1. So let's take a look at a simple example of addition and subtraction using basically the normal carry-borrow rules that we use for decimal addition and subtraction, only in this case, since we have base 2 numbers, we'll be doing things with only the digits 0 and 1. Here's an example. 63 plus 8 is, of course, equal to 71. The number 63 is represented by these bits. The number 8 is represented by these bits, and you should make sure that that makes good sense to you. And when we add them up, you'll notice we'll do a 1 and a 0 is a 1, a 1 and a 0 is also a 1, 1, 0 again is 1, but now a 1 plus 1 in this column yields a 0 with a carry of 1. So we now add 1, 0 plus the carry of 1 yields a 0 again, but a carry of 1. So we do 1 plus 0, again yields a 0 with a carry of 1. That ends up in this position. And this is the number 71, our result. To do subtraction, we do something very similar. Let's say we had the number 12 in binary, and we wanted to subtract 7. 7 is represented by 0, 1, 1, 1. And so if we do this subtraction, we would say 0 minus 1, of course, is a 1 with a borrow of 1. 1 minus 1 is a 0, and a 0 now because we borrowed earlier. A 0 minus 1 is a 1 again without, we leave this as a 0, so the result is 0, 1, 0, 1, which is in fact equal to the number 5, what we'd expect. Okay, so that's the basics of addition and subtraction in binary. So let's do the natural thing for representing positive numbers. They're going to correspond to all the unsigned integers of the same value. So in 8 bits, for example, we can go from the hex 00 to the hex 7F and represent 127 different positive numbers. But since we need about half of them to be negative, we're going to save the other half from 128 to 255 to really be used to represent negative numbers rather than those larger positive numbers. So we're going to use the high order bit, that B7, to indicate whether a number is negative or not. And often that most significant bit is the sign bit. This is called a sign and magnitude representation. Let me give you a few examples. Here we have the number 0, and you'll notice that it has a 0 in the most significant bit. So it's non-negative because the sign bit is 0 and the value is 0. Here we have another positive number, a non-negative number, where except for the sign bit, all the other bits are 1. That corresponds to the number 127. Okay? Now, the other two numbers in these examples are both negative numbers. They have a 1 in the most significant bit and can be used to represent, for example, a minus 5 in this case. This is the number 5, but we're saying it's negative, so we're going to basically just use that sign bit to say whether we put a minus sign in front of it or not. In this case, we have minus 0, which gets into one of the problems with sign and magnitude notations. There's the two representations for 0. The first line here was the positive 0. This is the negative 0. Well, they're really both 0, so this this will cause some problems for us if we use this representation. Okay, so let's talk about sign and magnitude negative numbers in a bit more detail. Here I'm showing a number wheel for 4-bit binary numbers. It starts at 0, 0, 0, and as we increment by 1, we move around to 1, 1, 1, 1, and of course if we continue to increment, we'd go back to 0, 0, 0, 0. Now, what I've also noted on the outside of the circle is the number corresponding to each bit pattern. So you see here we have our 0, 1, 2, 3, all the way around to 7, and then we have the negative numbers on this side with the first bit being a 1. Right? So a -1 in binary is always represented by the in sign magnitude binary with a leading 1 for the sign and then a value of 1 for the remainder of the bits, okay, for the magnitude. All right, so the unfortunate side effect of this, as we've said, is that we have two values that correspond to 0, a -0 and a +0. So why is this an issue? Well, it makes math a little cumbersome. Let's take a look at a little example. If I do 4 minus 3, that corresponds to the number 4 here, 0, 1, 0, 0, minus 0, 0, 1, 1. And if we do the arithmetic for that, of course we see that the value is 1. But now if we look at the 4 plus minus 3, which should yield the same result, we see that in fact 4 plus a minus 3 yields minus 7. Well, that's not the same as 1. So we now would have to worry about what order in which we do the additions and subtractions. This is not something we want to be dealing with when we think about arithmetic in our programming languages. So instead of using sign and magnitude numbers, computer systems today use what are called Tooth complement negatives. And let's go back to that representation of a -1. So instead of using the sign bit at the front to the most significant bit to just represent the minus sign in front of the 1, what we're going to do is give that most significant bit a large negative weight. All right, remember each of the bits has a certain weight corresponding to the column that they're in. So bits 0 through the second to last bit represent the values 1, 2, 4, 8, 16, and so on. But what we're going to do is have the most significant bit represented as the W minus 1 bit, or in this case would correspond to that B7 we had in our previous slide when W is equal to 8. It would actually add a negative weight to the number. In this case, the negative weight would be minus 128. 2 to the 7th is 128, and then minus 128. So let's take a look at an unsigned number here, 1010. That corresponds to 1 times 2 to the 3 plus 0 times 2 to the 2, and so on, to yield the number 10 decimal. In Tooth's complement, 1010 would be interpreted a little bit differently. You notice that now we have a -1 for the first bit, the most significant bit. All right, that's that large negative weight, in this case -8. So that when we add this up, we see that this corresponds to the negative number 6 in base 10, using Tooth's complement notation. So a -1 is represented as 1111, right? -8 plus 7 for the remainder. So that would add up to -1. All right, so that looks a lot like we've solved our problem here, because what we've essentially done is shifted our number wheel a little bit. So now the numbers are the same on the right-hand side. You see we go from 0 to +7, but the numbers with the leading 1 are now in a different order than they were before. We start at -1 up here, go around to -2 to -3 to -4, all the way to -8. What's important to note here is that now we only have one representation of 0, namely all the bits are set to 0. And you'll notice that -1 is immediately adjacent to 0. So it looks like things can flow on a number wheel by doing basic addition and subtraction and get that to work. For example, if I start at 2 and take 3 steps back, I do in fact get to -1. That wasn't the case with sign magnitude notation. The other nice thing about 2's complement notation is it's very easy to obtain the negative number from its positive magnitude. All I have to do is take a bitwise complement of the positive number and add 1, and that gives me the negative version of that original number. Interesting fact that makes it very easy to take the negatives of numbers. Okay, so let's take a look at 2's complement arithmetic in some more detail. What's nice about 2's complement is the same addition procedure now works for both unsigned and 2's complement integers, so we only have to build one kind of adder in our processors. Let's take a look at the example 4 plus 3. Here we have the positive number 4, the positive number 3. We do a straight addition and we get a result of 7. That works out well. On the right hand side we have -4 plus 3. Okay. You'll notice that when we add that up we get all 1s. That corresponds to -1. That's correct as well. Now let's take a look at the middle here. 4 minus 3, that's the example we did before. That should have yielded 1, and now with 2's complement numbers we have a 4 is 0, 1, 0, 0, but our -3 is 1, 1, 0, 1. And when we add this up we get the result 0, 0, 0, 1. Of course we do have a carry out of 1 that we're going to drop, and because we have our 4 bits of precision here. And the result is 0, 0, 0, 1. Exactly the value we expected to see. The dropping carry makes this modulo addition, so we say that this is addition modulo 2 to the w, or modulo 256 in this case, with w equal to 8. Or in the examples here, with w equal to 4, it's modulo 16. Why does 2's complement notation work out so well? Well, let's try to look at it a different way. Whenever we have a positive integer, we would like the negative number representation of that same integer to always add up to 0 if we sum it with the positive version. So let's take a look at the numbers 0, 0, 0, 0, 1. What do we have to add to that in order to get all zeros, right? So what we really want to be -1 is whatever bit pattern gives us that same result. And we know now that that in fact is the pattern all 1s, which when we add will cause a carry to ripple down this entire sequence of 1s to yield all zeros with a carry out of 1 that we'll be dropping and ignoring because we do modulo 256 arithmetic. In the case of the number 2, we want the number -2 here. What bit pattern would yield that? Well, we'd expect it to have a 0 here, so that 0 plus 0 would come out to 0. And then a 1 in the second position, so that 1 plus 1 is also a 0. And then a sequence of 1s to ripple that carry through. So a -2 looks like this value. Okay? And you'll notice that that's just the bit pattern of the number 2 complemented and then adding a 1. So if we complemented every one of these bits, we would get 1, 1, 1, 1, 0, 1, but then when we add 1, we would actually get this value here, which is our -2. And then for 3, it's the same situation. The pattern that would yield all zeros looks like this, which you'll notice again is just a bitwise complement of the original 3 plus 1 added in. Okay, so that's how 2's complement works. If we look at these numbers now in terms of the possible bit patterns that we can have in 4 bits from 0, 0, 0 to 1, 1, 1, 1, you'll notice that for the first 7 numbers, the positive values, signed and unsigned numbers are exactly the same. But now for unsigned, we continue on to 8, 9, 10, all the way up to 15, while for signed representations, the value that would have been 8 now corresponds to -8, and the value that would have been 15 corresponds to -1. Now, of course, both signed and unsigned integers have limits. There's only so far we can go until we run out of patterns to use. So for example, if we tried to add 6 plus 4, the result would be 10, and we could not represent that as a signed number. There's just not enough bits to do that. You notice that there is no pattern that corresponds to the number 10. If they were unsigned numbers, we could, because we have a pattern of 10 for 10. In C, we also use the notation 15u to signify an unsigned number. In this case, 15u plus 2u yields 17, and that would not fit into any of our representations, signed or unsigned. Okay, we can also have a number that is too small. For example, minus 7 minus 3 unsigned would yield, as signed numbers would yield minus 10. And you'll notice that there is no pattern for minus 10. We only get up to minus 8. And then if they were unsigned, we still have a problem, because 0 unsigned minus 2 would be a negative 2. Well, we can't represent negative numbers in unsigned format, so we'd be in trouble there as well. So the CPU, when it's given these kinds of arithmetics to do, will throw an exception, meaning it will signal that it got a number that it can't represent. And it does that for signed values, but most CPUs do not do this for unsigned values. And C and Java, both languages, will just cruise along and not bother checking that the arithmetic was correct or not. So you have to do an explicit check if you really want to know if the arithmetic worked out correctly. And we'll see that again later on. All right, just a quick visualization of what is going on here. If we start off with a 2's complement number that can go from minus 2 to the w minus 1 to plus 2 to the w minus 1, when we move it to an unsigned value or represent it as an unsigned value, of course those positive values stay the same, but the negative numbers now look like big positive values. Okay? And similarly, going in the other direction, if we start with an unsigned number, the smaller numbers can just move straight across to 2's complement notation, but the large positive numbers, the ones that start with that leading 1, now get interpreted as negative numbers if we think of the representation as 2's complement. So we have to remember which type of number we have in memory. Is it a 2's complement number, or is it an unsigned integer? And that's part of how we get into types in these different languages, data types in these different languages. Here we're showing the addition of two numbers can yield a value that's very negative or a value that's very positive. The values, again, that are in the mid-range can just move straight along, no problem, to the 2's complement representation. But the very large positive numbers get interpreted as negatives. The very large negative numbers end up getting interpreted as big positives. Okay, so that's where we would run into trouble in our arithmetic if we generate too large a number or too negative a number. Okay, some values to remember when we're thinking about integers is for unsigned values, we have a special value called umin, which is the smallest number we can represent. That's 0, the bit pattern of all zeros, and the maximum umax is, the unsigned max is all ones, obviously, and that would correspond to the 2 to the w minus 1. While in 2's complement, tmin is 2's complement minimum is the biggest negative number we can have, which would be the pattern of 1, all 0, followed by all zeros. And then tmax is a 0 followed by all ones. So the maximum number is only half as big as it was for the unsigned values. And a negative 1 is represented by the sequence of all ones, FFFFF, if we were doing 32 bits. Okay, so for a word size of 16, we would see these values for umax, tmax, and tmin. These would be the hex representations of them and their binary representations.